Great, thank you. So in this room, I don't need to explain why we want AI and blockchain to work together. But as a person who has spent a lot of time and still thinks every day about designing protocols, designing systems and chains to serve the needs of users, I want to ask the obvious question that follows from the desire for AI, at least for me, which is what does AI need from our chains and how can we provide that? And of course, in thinking about this, really you can kind of divide the question into two different pieces. One piece is about off-chain AI, where you have an AI agent that sits off-chain and participates in the chain as a user. And then second, on-chain AI, where you have an AI model that is evaluated on-chain so that you get the accountability and transparency of on-chain activity for the model. And these are very different questions, very different problems. And so I want to kind of break the talk into two pieces. First, talking about what do we need to better support off-chain AI agents, and then I'll come back to the more technically difficult question of how to do on-chain AI model evaluation in a way that it is affordable and scalable. All right, so first, what does off-chain AI need? What off-chain AI needs mostly is what off-chain users need. And that's simply a network that is aligned, which to me means alignment just means making our stack, in our case the Ethereum stack, faster, cheaper, more reliable, and easier to use for users and developers. That's ultimately what I spend my days and our team spends our days doing. Now, when we add off-chain AI agents as users, we're simply saying that some of the users of our chain are AI agents. And AI agents, they want as users, they want all of these things as well. But some of them, they probably want more. For example, our notion of what is fast may be different for an agent than it is for a person. A person probably doesn't care much about speed below, say, 100 millisecond latency. But an agent might want latency much lower than that. And so agents may care more about speed. They may care also more about cost because an agent, say in a DeFi market, may be more active than a user would, do more transactions in less time. And therefore, cost becomes very important. Of course, reliability and ease of use. Reliability means the same. Ease of use is a little bit different. There we're talking about APIs and what are the technical affordances. But basically, faster, cheaper, easier to use is where we're going. Okay, now again, in this room I don't need to explain where all of this is heading. The combination of trading agents plus very low friction trading, low cost, high speed, leads to a kind of Cambrian explosion of DeFi capabilities, where DeFi products and DeFi assets are much more active and flexible and fluid, and you see a lot of innovation. Okay, so how can we make this faster? There's a whole set of things we need to work on to make our chains faster. Just to start, Arbitrum is the fastest blockchain technology, blockchain stack. There are Arbitrum chains running today at 100 millisecond block time. So it's very interesting that some people are celebrating having reached 250. In any case, Arbitrum has been there for 4 years. Let's set that aside. Okay, so what do we need to do to make it even faster? First, we need to have benchmarks. We want to have standardized benchmarks we can use to measure realistic performance. Not what is the biggest TPS number we can claim with a straight face, but what happens when we run realistic workloads on a state of realistic size with a realistic number of users. Second, we need to figure out how to make execution faster. How can we make the execution of virtual machines faster? How can we make database access in the nodes and validators more efficient, and all of those things. Third, how can we get parallelism? How can we discover and exploit parallelism in the workload? We don't want to make programmers work hard to think about parallelism and race conditions and all of that. What we want to do is discover the parallelism that's there, naturally exploit it, make the chain run faster. Resource pricing, this is an interesting one. People think about gas pricing and gas limits as what limits, of course, the throughput of chains. But really what's going on underneath that is that chains are keeping track of resource usage, comparing it against what they think a node can do, and then hitting the brakes by raising price when it looks like the resource usage is beyond what a node can handle. But if we're more careful about monitoring resource use and more careful about comparing it to node capabilities, then we don't have to hit the brakes so quickly. If we have anti-lock brakes, we can drive faster and still be safe. So better pricing, better resource accounting, thinking more analytically about what nodes can do, we can squeeze out a surprising amount of extra performance on the same hardware. And then finally, sharding, meaning horizontal scaling, having many chains and being able to do that with less friction. Horizontal scaling has been pretty successful so far. There are something like 130 chains currently that are using the Arbitrum stack. Here are some representatives. Other L2 stacks could put up similar slides. There are at this point hundreds of L2 and L3 chains that are either active or under development and close to market. So, and this has led to a huge increase in the capacity of the Ethereum stack. Depending how you count, anywhere from 30x to 100x increase in the capacity and the actual traffic, the amount of gas, number of transactions, amount of data, et cetera, handled by the Ethereum stack. So this has been very successful, but the other thing that I said on the previous slide about horizontal scaling is that it needs to be smooth, and I'll come back to that. All right, how can we make it cheaper? At the end of the day, the cost, the fees that you pay on a chain are going to be governed by the cost of actually operating the chain, right? A chain has to be a going concern. VC subsidies will only last you so long. In the long run, if you want fees to be lower, you have to make it cheaper to operate the chain. And we're focusing on that a lot. I talked earlier about better pricing. Don't hit the brakes unless you need to. All right, so we have a lot of chains out there. How can we connect all of them? That's one of the huge problems. And by the way, if we think about AI agents acting on these chains, agents are likely to want to do cross-chain stuff probably more than users. Why? Well, because users have limited attention. An agent might be looking across hundreds of chains, looking for opportunities. Oh, I have an asset over here, I'd rather have it over there. I have an asset over here, I'd like to use it in a DeFi market over there, and so on. So we expect that with the growth of AI agents, we'll see more demand for cross-chain activity, and the AI agents will want that to be fast, trustless, and reliable. Okay, so how are we going to do that? Well, here I think we can take a lesson from the internet. The internet is the best example of widespread, trustless, open interoperation that has ever been built by people. And so I think we can learn a lot from it about how to build a robust and safe, open interop ecosystem. So internet-style interop has a bunch of features. It's fast. It's standards-based. It's asynchronous, meaning that you don't stop and wait for the other entity to act, because who knows how long it will take, or indeed whether it will ever respond to your query. You don't stop and wait. You try to keep multiple balls in the air at the same time. It's fault-tolerant, meaning that one unit does not assume that the other units will be there, will work correctly, will even respond at all. And it's security conscious, meaning that one unit doesn't assume that the other unit or units that it's interacting with are necessarily secure. You can trust if you want, but you should trust but verify. In the blockchain setting, that means we want this to be trustless, so that people don't have to worry about intermediaries, they don't have to worry about other protocols and whether they work or not. Now that is a tall order to provide all of that, but I think we can, and our research is starting to show how we can do that. In the Arbitrum research community, the Offchain Labs research team, we've been working on a concept called the Universal Intent Engine, which is basically an open framework that allows parties who want to have cross-chain opportunities, actions to be done, to publish intents, which can then be fulfilled by solvers in a sort of standard model. But the magic here is not so much that concept. It's about putting in place the APIs and putting in place the mechanisms so that anyone can use this across the broadest range of chains, the broadest range of applications, and the broadest range of settlement rails. We're trying to build the largest tent we can for interop and build it in a standards-based way. So all of those things, and of course, as I said before, this has much in common with what users want, ordinary non-agent users want from their blockchains. These are the things we're working on and will continue to need to work on. But let me turn the page and talk about on-chain AI. and ask, what does on-chain AI need to be really practical, right? And the short answer is what it needs is proving. If you're operating a chain, you can, in a node, evaluate a model, and you can do that in whatever's the fastest way you have, using whatever equipment, whatever hardware, whatever GPU farm you want to. But at the end of the day, if we're going to do this on-chain, we need to be able to prove what is the correct result of evaluating some model against some data. And there's several steps to this, which I want to break down and spend a bunch of time talking about, because it's both an interesting technical problem and also one that is not fully solved. So one of the first things you need to do in order to get proving of an AI model is you need to guarantee that there is a unique correct answer. So those who are embedded in kind of the details of how AI model evaluation works, you probably know that evaluation of a model is slightly non-deterministic. That is, you can evaluate the same model on the same hardware, and you get answers that are very, very close, but not identical. What is the reason for that? Well, when you're evaluating, there are different activities that are being done in parallel, and so you're doing all the same arithmetic, but you're doing those arithmetic steps in different orders. And floating point arithmetic, the standard way of doing this, doesn't behave like textbook arithmetic. It's not commutative and associative. That means it matters in what order you do the operations. So if you have multiple GPUs, for example, working on different parts of the problem in different orders, might get different answers. Can't have that if we need to prove there needs to be one correct answer, right? So we need to take that technical step. Suppose we've done that, though. Now, how then can we prove on-chain what the result is of evaluating a model which we've now made deterministic? There's basically three approaches if you break it down, and I want to talk a little bit about each one of them. And these are the same three approaches you would use to prove, same three general approaches you would use to prove ordinary computation on-chain. We're just going to adapt and specialize it for proving the evaluation of an ML model. So the first approach is the approach that, say, Ethereum uses, which is what I'll call staking plus voting. That is, you have validators who stake, and in one round of the protocol, someone makes a claim about what the correct outcome is. Everybody else, the other validators, vote thumbs up or thumbs down. If the proposal gets enough votes, it's accepted, it's treated as correct and true, and on you go. If there are enough votes against, then it's rejected, and the proposer gets slashed. They lose their stake. So an important thing to recognize about this is that you win, the proposer wins, not by being right, but by giving a result that gets enough votes, by being popular, if you will. And that means that you can cheat if you can arrange to have enough votes in favor of your approach, whether that's by bribing or cheating or hacking or just tricking people into voting for something that's not quite true. So if someone tries an attack against this scheme, it might work. And if the attack does work, then the attacker won't get slashed, right? So attacks sometimes work, so you might sometimes get slashed. Now, if you have a very large consensus that's backed by very deep staking, like on Ethereum, this approach can actually be quite secure and really excellent. But if you try to cut corners and you have a small committee and the stakes are relatively small because you want it to be cheap to operate, now you're getting into dangerous territory. Okay, that's the first approach. Second approach is the approach that is taken for ordinary computation by optimistic rollup stacks like Arbitrum or OPStack. And this is staking plus optimistic proving. What that means is someone can stake on a claim about what is the correct outcome. Somebody else can show up and say, no, the correct outcome is something else. I'm staking on that. And then critically, if there is a dispute, the protocol will figure out who's correct on the merits. And the party who's correct on the merits will win, and the other party will get slashed. And the beauty of this is that it's very cheap to do in the common case because people don't like to stake on false things when they know they'll get slashed, right? And so the advantage is the attack will not succeed, and the attacker will get slashed. And therefore, a rational party will never, if people are rational, you will never even have a dispute. The final approach is ZK proving. That, of course, is much more expensive to do, probably too expensive to do for realistic size ML models, at least today. It has the advantage of an attack will not succeed, and it doesn't even need staking. But what it does need is the expensive generation of a proof every single time. Okay, so can we just, well, how about we just evaluate the model on chain? We'll just write some code in Solidity. If you're using Arbitrum, you write it in Rust and compile it to Stylus. Can't we just run that on chain? That works great if it fits at all within the gas limit, if you can afford the gas. But for a realistic size model, that's probably not going to work. It won't fit. All right. So can we evaluate the model in a coprocessor? Yeah, we can. We can use the advantage of a coprocessor, some sort of box on the side of the chain, if you will, that has special functionality, is that you can use customized proving gadgets or customized proving protocols. The disadvantage is there's some complexity and integration requirements. Fact of the matter is, in practice, we probably have to suck it up and deal with that complexity and integration difficulty, because a coprocessor seems like the more practical approach. Okay, so if we're doing that, how can we think about optimistic proving with a specialized proving protocol for proving ML model execution? So here's how this might work. So imagine that you have an ML model that consists of a bunch of neuron units. Each one is taking a weighted sum of a bunch of inputs with known agreed upon weights, and takes that weighted sum, runs it through some simple activation function, and that's one unit. You have some large feed-forward network of those, right? That's the sort of the standard model. So first, the parties commit to cryptographically to the outputs of all of the units in the network. And now, if two parties make different commitments, they must have different opinions about what at least some of the units output. You then use a sort of standard bisection protocol where you essentially ask the parties, okay, give me a commitment to the first half of the network. Give me a commitment to the second half of the network. By doing that, you can figure out, oh, they must disagree in the first half, or their first disagreement must be in the second half, right? You've cut the size of the dispute in half. Do that over and over. Pretty soon, you've narrowed down the dispute to one unit. There's a dispute about evaluation of one unit of the network, and that's the first place they disagree. Okay, then you just need to figure out, okay, who's right about that unit? And you can, again, the evaluation of that unit is a giant dot product, a bunch of multiplications and additions, and then the simple activation function. You could, again, bisect over the terms of that dot product, again, a logarithmic number of times, narrow it down to just a single multiply and add, or just to the evaluation of the activation function. This works great. It's very feasible. You can implement it in the lab, and this, if I had to implement something today, this is what I would do. Okay. Finally, you can go to ZK proving of model evaluation, and that can certainly work. It's generally true about ZK proving that you can prove anything if you have enough GPUs, and that's kind of the case here too. So the main challenge here is not can you do it. The main challenge is how much it costs to do it. And you can try to be clever. You can say, well, you know, there are specialized gadgets we can use for doing cheaper ZK proving of these sort of weighted sums or inner products, if you will. And there's some things you can do there, but still this is probably too expensive. Even with a specialized gadget, that's where we are. Okay, so there's a lot of work still to be done. I think we've made some progress understanding how to do proving of on-chain model evaluation. But still much work left to do, and we look forward to working with folks in the community to try to figure out how to get that done and deployed. And I'm required to end every talk with the Arbitrum mantra: your chain, your rules. Thank you.